Welcome to the series of lecture on finite element analysis. In this part, we are going to derive the element characteristic equation of a beam problem. In the last part, we derived the governing differential equation for a beam. So the governing differential equation is a fourth order homogeneous differential equation. So ei d power 4y by dx power 4 minus w is equal to 0, where E is Young's modulus, I is moment of inertia of the cross section, Y is the transverse deflection, W is the load intensity of the uniformly distributed load. First, we are going to convert the weak form of this governing differential equation. Since the governing differential equation is of the order of 4, if we want to solve this problem as it is, we have to use a minimum order of polynomial is fourth order polynomial. To reduce the order of polynomial required to solve this problem, we are going to convert this governing differential equation of a beam into a weak form. How to convert a governing differential equation into a weak form? We have already discussed in the earlier part. When we substitute a trial function in the governing differential equation, then the governing differential equation going to be a residual function. So why? Because if you substitute the exact solution to this governing differential equation, then only the equation will be satisfied. That means right hand side will be equal to 0. But when you substitute any trial function for this governing differential equation, this equation will not be satisfied. That means it will not be equal to 0. So it will give some residue. That is why it is called a residual function. When a trial function is substituted in governing differential equation, then we will get the residual function. After getting this residual function r of x, we are going to use the Galerkin approach. This is the Galerkin equation. R of x should be multiplied with one weight function. Here weight function is denoted as v of x. This product should be integrated over the full domain. It should be equated to 0. This is called the Galerkin equation. We will substitute the r of x of our beam problem. Integral 0 to L ei d power 4y by dx power 4 minus w v of x. Since w is used load intensity, we are using v of x as for the weight function, which is equal to 0. Integral 0 to L ei d power 4y by dx power 4 minus w multiplied by weight function v of x dx is equal to 0. When you multiply this v of x into this bracket term, so this integral will be splitted into two. First, integral 0 to L ei d power 4y by dx power 4 v of x minus integral 0 to L w into v of x dx equal to 0. This fourth order differential operator is present inside the integration. So this is called the integro differential equation. By applying integral by parts formula, we can reduce this fourth order differential operator into integral by parts formula. Integral u dv is equal to uv minus integral v du. For our case, what is u? U as v of x, d by dx of d cube y by dx cube. We will take the ei also inside the differentiation. Your dv will be d by dx of ei d cube y by dx cube. Like u is v of x. When you take u is v of x, then du will become dv. dv is considered as d by dx of ei d cube y by dx cube. So we will get v is equal to ei d cube y by dx cube. This du and this v will be used for writing this right hand side equation. So first we have to write u v, then minus integral v du. The first part is u v, we are applying the limit, then minus integral v du. Then the second remaining part minus integral 0 to L w v of x dx is equal to 0. You see in this, the fourth order differential operator is reduced to the third order. We have to apply this integral by parts formula once again. Then this third order of differential operator will be reduced by second order. So before that, we rearrange these terms. Ei d cube y by dx cube. What is the physical meaning of this one? Third order derivative of the transverse deflection is nothing but shear force. So that is why this is replaced as shear force multiplied by weight function, then 0 to L minus ei dqy by dx cube dv by dx into dx. This term, this integral term is taken to the other side, so integral 0 to L w v of dx. We are keeping this integration on left side and take this term to the other side, so minus integral 0 to L ei dqy by dx cube dv by dx. Now integral 0 to L w vx dx minus, we are taking this term to the right hand side, so q of x v of x 0 to L. For this left hand side integral, again it is a integral differential equation. We are going to apply the integral by parts formula again. So by considering this part as dv, this as u. Okay, so integral u dv, when you apply this one, the third order differential operator will be reduced by half. The integral by parts formula again, integral u dv uv minus integral v du. U is equal to dv by dx. The dv is taken as d by dx of ei d square y by dx square. Since u is dv by dx, your du will become d square v by dx square. From this, v is equal to ei d square y by dx square. First you will get uv. So uv, since the negative sign is there in this equation, so first we are getting this negative sign minus uv. U is dv by dx, v is ei d square y by dx square 0 to L. Then minus integral v du, so minus become plus here, integral 0 to L ei d square y by dx square d square v by dx square. So this is v du. So du d square v by dx square dx. Then right hand side we are writing integral 0 to L w v of x dx minus q of x v of x 0 to L. What is this dv by dx? dv by dx is nothing but first order differentiation of the function v. This is going to be called as slope. And what is ei by d square y by dx square? This is second order derivative of the transverse deflection multiplied by the ei. This is nothing but a bending moment. This term going to be written as m of x. This is theta of x. Keep this integral in the left hand side and take this part in the other side. We get the final equation, integral 0 to L ei d square y by dx square d square v by dx square dx equal to, then first integral 0 to L w v of x dx minus q of x vx 0 to L plus this term is taken here m of x theta of x 0 to L. Now this is the weak form of governing differential equation of beam problem. Why it is called weak form? In the actual governing differential equation, the order of differential operator is 4. That order of differential operator is reduced by half. Here the order of differentiation is only 2. That is why it is called a weak form of the governing differential equation of beam problem. We will see the physical meaning of this equation. What is the physical meaning of this left hand side part? In Rayleigh's method, we have seen that the equation for strain energy of a beam is ei by 2 d square y by dx square whole square dx, right? This is similar to that one. This indicates the strain energy stored in the beam. Coming to the right hand side, w is the udl, the load intensity of the udl multiplied by this function v of x, weight function. So this is nothing but load multiplied by the displacement function. So this is going to be a work done due to the uniformly distributed load. Coming to this part, q of x is the shear force multiplied by a function, displacement function. Again this is going to be work done due to shear force. Similarly here, m is the bending moment, theta is the slope. What is slope? Slope is nothing but angular displacement. So bending moment into angular displacement, this is work done due to the bending moment. This equation is indicating total potential energy of the beam. Strain energy is equal to work done. That is a potential energy theorem. We have 3 parts of work done. One is work done due to the self weight. That is UDL is considered as self weight, and work done due to the shear force, work done due to the bending moment. This shear force and the bending moment term going to be called as boundary term in finite element method. Here this part going to give the stiffness matrix of the beam, and here we will get the force vector, and this term going to be considered as the boundary term. Since the order of differential equation is reduced by 2, so we can solve this problem by using the second order polynomial itself. That is the advantage of the weak form. After this stage, we are going to introduce finite element concept here. For beam also, we are going to use the one dimensional line element. Here we are going to use the 2 degrees of freedom, transverse deflection W, and the slope theta. We need minimum 2 degree of freedom for complete definition of a beam problem. That is why here we are using transverse deflection W and the slope theta as a 2 degree of freedom. When we use the line element at each node, we are going to consider these 2 degrees of freedom W and theta. For node 1, we will get W1 theta 1, node 2 will get W2 theta 2. This is also a one dimensional line element, but we are using 2 degrees of freedom at each node. So the total degree of freedom of this element going to be 4. For this element, we are going to derive the 4 shape function. So when the one dimensional element is used for solving a beam problem, it is called a beam element. So when one dimensional element is used for solving bar problem, it is called a bar element. Total degree of freedom for beam element is 4. Now how to derive the 4 shape functions we will see. For deriving the shape function, first we have to assume a trial function, that is a polynomial trial function. Since we want to derive 4 shape function, here we are considering the polynomial function having 4 unknown coefficient a0, a1x plus a2x square plus a3x cube. From this equation we can understand that the transverse deflection of a beam is defined by third order polynomial. So that means it is a non-linear function. When a beam is subjected to transverse load like this, let us say the load is acting like this, it is going to have a deflection like this. It is called a bending. This deflection is in curvilinear form. To define this deflection, it is better to use a non-linear polynomial. So here also we are using the third order polynomial, which will be a best suitable function for defining this curvilinear behavior of the field variable w of x. That also we have to understand. When we use this third order polynomial, it will define this transverse deflection, behavior of the transverse deflection more accurately. This w of x equation, let us write it in matrix form. So keep this coefficient as the column matrix, a0, a1, a2, a3, and the x terms are made as a row matrix. So 1 x, x square, x cube multiplied by a0, a1, a2, a3. These are called the unknown coefficient matrix or Ritz coefficient matrix. Since we have another degree of freedom theta, so what is theta? By definition it is a dw by dx, first order derivative of the transverse deflection. So when you differentiate this one, a0 will become 0, you will get a1, 2a2 x, then 3a3 x square. This is for the theta. So there are 4 unknown, a0, a1, a2, a3. If we want to solve this 4 unknown, we need a 4 simultaneous equation. How to frame the 4 simultaneous equation? We are going to use the boundary condition for this beam element. So for this one dimensional beam element, we have boundary conditions like this. At node 1, we have degree of freedom w1 theta 1. Node 2, we have degrees of freedom w2 theta. We are using the local coordinate system. At x equal to 0, it is node 1. At x equal to L, it is node 2. At x equal to 0, w is w1, theta is theta 1. This is the two value nodal parameter. When you put x equal to 0 in this equation, we will get a0. So w1 is equal to a0. That is what written here. W1 is equal to a0. Similarly, when you put x equal to 0 for this equation, you will get a1 is equal to theta 1 is a1. So the two value a0 and a1 evaluated now. we use the remaining two condition. At x equal to L, W is equal to W2 and theta is equal to theta 2. We have to substitute x equal to L in this equation. A0 plus A1L plus A2L square plus A3L cube. That is what written here. A0 plus A1L A2L square plus A3L cube. Similarly, at x equal to L, theta. We have to substitute x equal to L here. A1 plus 2A2L plus 3A3L square. That is A1 plus 2A2L plus 3A3L square written here. Now we have four equations. So you have to write in matrix form. When we use the matrix form, it is easy to solve. So this is the equation. So the nodal parameter W1 theta 1 W2 theta 2 is equal to the unknown coefficient matrix A0 A1 A2 A3. So this is written as a 4 by 4 matrix. This is a 4 by 4 matrix. This is 4 by 1 matrix. 4 by 1. So we will get 4 by 1. If you want to find this unknown coefficient matrix, you have to take this 4 by matrix to the other side and multiply with this nodal parameter matrix. You will get the A0, A1, A2, A3 value. How this matrix is written? Here you see 1 0 0 0. So if you multiply with this one, A0 will be equal to W1. Similarly, second row, when you multiply this one, A1 will be equal to theta 1, like that. So third row will give you W2 value. So this equation, these four equations are written in matrix form. Let us say this is the matrix C. Then A is unknown coefficient matrix, U is the nodal displacement matrix. Now when you take this C matrix to the other side, then it will be C inverse. You can easily find the unknown coefficient matrix A is C inverse multiplied by nodal displacement U. To save the time, I am directly giving the C inverse matrix. So this is the inverse of the C matrix, which is determined using the standard procedure. So first we have to find a cofactor matrix, and inverse of the cofactor matrix is nothing but adjoint matrix divided by the determinant. After knowing the C inverse, then we substitute this A in the first equation, that is W of x equal to 1 x x square x cube and the C inverse and W1 theta 1 W2 theta 2. Multiplying these, this is a 4 by 4 matrix. This is actually 4 by 4 matrix. This is a 1 by 4 matrix. So multiplying these two matrix, we will get again a 1 by 4 matrix. This is going to be called as shape function for this beam element n1, n2, n3, n4. How do you get this one? This row matrix multiply with this first column. So you will get 1, this 0. So 1 minus 3 by L square x square plus 2 by L cube x cube. This is going to be the shape function 1. Like that, if you take this row matrix, multiply with the second row, we will get n2. Then multiply with the third row, we will get n3. Multiply with the fourth row, we will get n4. I will show the final shape function. So shape function 1, n1. This is shape function for node 1. 1 minus 3 x by L whole square plus 2 x by L whole cube. And n2 is x minus 2x square by L plus x cube by L square. n3 is equal to 3x by L whole square minus 2x by L whole cube. n4 is equal to minus x square by L plus x cube by L square. These are the shape function we are getting for the beam element. The shape functions are in the third order. If you see this one, all the shape function we have x cube term. So since we have assumed a third order polynomial, we are getting shape function also in the third order. And out of these four shape function, n1 and n3 are for the displacement. Here you see, this is w1 and w2, right? n1 and n3 for displacement w1 and w2, and n2 n4 is for theta. You see the graphical representation of this shape function. n1 n3 are the shape function for the displacement, n1 n2 n4 shape function for slope. We know the properties of the shape function. On its own node, the shape function will take a value of 1. So if you take this shape function n1, so n1 will take value of 1 at node 1, and other node it will be 0. This node 2 will be 0, but here if you see the variation of this n1, it is a non-linear variation because the shape function is a third order polynomial, so non-linear variation. Similarly n3, so this is n3. For n3 at node 2 it will take a value of 1 and it will vary non-linearly. Node 1 it will be 0. So we will see the variation of the shape function n2 and n4. It is for slope. So this is at node 1, n2 is varying like this, n4 is variation is like this. For displacement as well as slope we are getting the non-linear variation, which will be going to give a better solution for this beam problem. We are defining the element characteristic for this beam problem. So it is a one-dimensional line element. The number of node means we are assuming only the primary end nodes. So node 1 and node 2, and the degree of freedom at each node we are assuming 2 degree of freedom, w1 theta 1 and w2 theta 2, like that. So total degree of freedom is 4. Total degree of freedom is 4. So we are getting 4 shape function n1, n2, n3, n4, like that. So after deriving the shape function, now we will go to the derivation of the element characteristic equation. Already we derived the weak form of the governing differential equation of beam problem. So here I am writing the weak form once again. Integral 0 to L ei d square w by dx square. Here w is taken as the transverse deflection. That is why load intensity we are using f naught. Slight change you have to understand. Since w is given to transverse deflection, we are using f naught for the load intensity. Ei d square w by dx square, d square v by dx square dx. V is the weight function. Then right hand side we have integral 0 to L f naught v of x dx minus q of x v of x 0 to L. This is a shear force, and the m of x theta of x 0 L bending momentum. We are going to use the one dimensional line element to solve this problem. For this line element, what is the interpolation function we are going to use? The w of x, right? W of x inside the element, it will be equal to n1 w1 n2 theta 1 plus n3 w2 plus n4 theta 2. So these four shape function we derived now. Using this shape function we can interpolate the transverse deflection value any point inside the element, right? This is the interpolation function, and we are going to use the weight function as n1 n2 n3 n4. When we substitute w of x here, w of x is equal to n1 w1 n2 theta 1 plus n3 w2 plus n4 theta 2, and your weight function v of x, when you consider first weight function as n1, we will get one simultaneous equation. When you substitute v is equal to n2, we will get the second equation. By substituting n3, we will get the third equation, and n4 will give you the fourth equation. Arranging all the four simultaneous equation in matrix form, that is going to be element characteristic equation for the beam element. When we substitute this n1, n2, n3, the shape function will be differentiated two times, right? So the differentiation I am showing here. So if you take n1 is equal to 1 minus 3x by L whole square plus 2x by L whole cube. So when you differentiating this first, dn1 by dx is equal to 1 will be 0. So you get a 6 minus 6 by L square x plus 6x square by L cube, right? 6 by L cube x square, like that. So again you are differentiating the second time, you will get minus 6 by L square x will become 1, then here 12 by L cube x, like that. If you differentiate n2, dn2 by dx, d square n2 by dx square, like this. N3, differentiating n3 two times, we are getting this expression. Differentiating n4, dn4 by dx and d square n4 by dx square. All the second order derivative of the shape function is required to form the element characteristic equation. Now I'll give you one element of the stiffness matrix and one element of the force matrix. So then finally we will write the element characteristic equation. This left hand side part going to give the stiffness matrix of the element characteristic equation. The right hand side we are going to get the force matrix. I will tell you how to formulate stiffness matrix and the force matrix for the beam element. In case of the stiffness matrix, the size of the stiffness matrix is going to be a 4 by 4 matrix. How? When you substitute the W of x is equal to this expression, weight function as n1, n2, n3, n4, we get 4 simultaneous equation, and for each equation we have 4 part n1 w1 plus n2 theta 1 plus n3 w2 plus n4 theta 2. When you expand this one, you get a 4 integral part. One equation we get 4 element, that is elements of row. So I will explain how the element of the stiffness matrix is derived. Take only one element. Similarly, in the force matrix also, we will see the right hand side force matrix. We will see how the elements of force matrix is derived for only one element. This is going to be written as Kij, which is going to be stiffness matrix. So this is Kij integral Ei d square ni by dx d square nj by dx square dx. In this, we need a second order derivative of this shape function. For that reason only we derive the second order derivative here. When you write the k11, the first element, then it will be integral 0 to L ei d square n1 by dx. D square n1 by dx already we found out. So minus 6 by L square plus 12 by L cube x. Substitute that one. Again this d square n1 by dx square. We are substituting that value. Multiply these two bracket terms, you will get 4 terms. Ei 36 by L power 4 minus 72 by L power 5 x minus 72 by L power 5 x plus 144 by L6 x square dx. You simplify this term. So 144 by L6 s square and the x part is added. So we get minus 144 L power 5 x plus 36 by L power 4. Now do the integration. Ei is taken outside. So 144 by L6. So x square will become x cube by 3. Similarly here x will become x square by 2. So here you will get x. Apply the limit 0 to L. So you will get Ei 48. This is 144 by 3 is 48. So here L cube by L6. So you will get L cube. Here 144 by L cube. Here 2 is there. So 144 by 2 is 72. Square by L5. So you are getting L cube plus 36. Here L by L power 4. So you will get L cube. So on simplifying this, finally we are getting 12 Ei by L cube. So this is the one term of the stiffness matrix. If the stiffness matrix is a 4 by 4 matrix, the first term alone we are evaluating. So K11 stiffness matrix K11 we are evaluating, it is 12 Ei by L cube. Like that, if you want to find the K12, how to form this K12, we have to substitute integral 0 to L Ei. Here d square n1 by dx, d square n2 by dx square dx, like that. So we have to substitute the d square n2 by dx square, which is already we evaluated. You have to substitute this one. Then we will get k12, k13, like this. Like this we can evaluate all the 16 components of this stiffness matrix. Coming to the right hand side, evaluation of load or force matrix. So in general it is given as integral 0 to L f naught nj dx, right? So this is, instead of v of x we are using the shape function as the weight function. We will take first f1 alone. F1 integral 0 to L f naught n1 dx. So you have to substitute the shape function n1 value. Now integrate this one. To take the f naught outside the integration, 1 will become x. Here x square will become x cube by 3, x cube x power 4 by 4. Then apply the limit 0 to L. After that you will simplify this. You will get F1 is equal to F0 L by 2. Similarly, we can find the F2. So how do you find F2? F2 is integral 0 to L F0 N2 dx. On the right hand side, it is going to be a 4 by 1 matrix. So here you will get F1, we evaluated now. Similarly, you will get F2 and F3, F4, right? So if you substitute N1, N2, N3, N4 here, we will be able to get these 4 elements of the force matrix we can find. After evaluating all the elements of the stiffness matrix and the force matrix, the final element characteristic equation will be like this. EI by L cube will be taken common. So here we are getting this EI by L cube. So 12. 12 is considered. EI by L cube will be the common term in all the elements. That is why it is taken outside the matrix EI by L cube. And in here you will get 12, 6L minus 12, 6L, 6L, 4L square minus 6L, 2L square minus 12 minus 6L, 12 minus 6L, 6L, 2L square minus 6L, 4L square, like this. These are the elements of the stiffness matrix. Now the nodal parameters are W1 theta 1, W2 theta 2. Coming to the right hand side, we are getting the F0 L by 2. So for the second term also we will get this as common. So that is why we are getting F0 L by 2, 1 L by 6, 1 L by 6 plus the boundary terms. So boundary terms are the shear force and the moment. So F1 M1 for the node 1, F2 M2 for the node 2. So any external force or external moment is acting at that particular node, we have to consider that as the boundary term. So here, so this will be the element characteristic equation for this beam problem. So in general we can say this is stiffness matrix K and this is displacement matrix U and the force matrix F. For a beam problem, the element characteristic equation is like this. Your stiffness matrix size will be a 4 by 4 matrix. Why we are getting 4 by 4? Because the total degree of freedom for the beam element is 4. So W1 theta 1, W2 theta 2. That is why we are getting 4 by 4 matrix. And this is the force matrix is also 4 by 1 matrix. And if you see the stiffness matrix, the properties are, it is a square matrix and a symmetrical matrix. Square matrix and a symmetrical matrix. Here the theta is also involved here as the degree of freedom. So we cannot get the property, that is by adding elements in a row and elements in a column will not be 0 here, because it is theta 1 is there. We differentiated the transverse deflection. So this is the derivation of element characteristic equation for a beam problem. In the next part, we will see how to solve a beam problem using this element characteristic equation. Thank you for your passion listening.